Hello, this lab is on the central limit theorem and confidence intervals. So let's get right into it. Go to your Geography 316 folder and open your R project. Go away. And then from there, you will create a new script, save it. Your last name, this is lab 9. And then first things first, don't forget to load the tidyverse. All right, so central limit theorem. So stats didn't really start making sense to me until I learned about the central limit theorem, which is beyond me why I wasn't taught it in my first stats class. Maybe I was and I just don't remember. But I always wondered, so you learn all of these statistical tests, but so what? What do they mean? Why are they true? What is like the natural law that makes it so that we can believe what these statistics have to say? And a lot of that has to do with the central limit theorem. So what the central limit theorem states is that even if a distribution of a population is not normal, say it's skewed to the right, skewed to the left, if you repeatedly take samples from that population, for each sample, you calculate the mean, then you plot the distribution of those means. That distribution of the means will be normal, no matter what the distribution of the original population, the distribution of the sample means is going to be normal. And that's why we can do a lot of these tests. Most of them, for the most part, are comparing means in some way. And so because those means come from a normal distribution, and we know things about the normal distribution, its characteristics, its probabilities, that's why we can say things about the population based on samples. And that is the basis of inferential statistics. So to go through it here, this calculation here is for the standard error of the mean. And so that just means the standard deviation of those means that you're calculating. So for all of those samples, you calculate their mean, you plot the distribution, the standard deviation of that, the standard deviation of the distribution of the means is called the standard error of the mean. And so I know this looks complicated, but to break it down, this just says X bar is the mean of X. So X bar, which is those means of the sample populations, this tilde means distributed as, and then this N means normal. So the means are distributed as a normal distribution characterized by a mean of mu, we've seen that before, and a standard error of the standard deviation over the square root of N. All right, so, and I just give that there because you may see it at some other point and I want you to know what it means, okay? But this is characteristic of the sample means. And so you can see here, because the standard error is the standard deviation of that sample divided by the square root of N, as N increases, which means as your sample size increases, the standard error is going to become smaller. So the higher your N, the less variance there is going to be in your distribution of the means, which translates to you're more confident in your estimate of the mean of the population. All right, so first, like we have been doing, we are going to create a population. So this should all look familiar to you at this point. You're going to set your seed so that we all get the same values from this. set the seed. All right, run that. And then you're going to create a population, and this is what we will sample from. So a population with a normal distribution, we are going to do 10,000 draws from that normal distribution. The normal distribution is characterized by a mean of 100 and a standard deviation of 5. Let's run that. You can see that has come up in my environment here. It's population. So we can also take the mean of that population, just to see it. Let's print it so you can see. Gosh. Oh, what's going on there? Oh, sorry. Pop mean is the name of the variable. There we go, pop mean. So you can see it's very close to 100. The only reason it's different is because, again, this is a random. We're doing 10,000 random draws from a theoretical normal distribution. And so now this is just a quick and dirty histogram. You don't always need to make it look nice like the way we do with ggplot. Well, if you ever see this error, that just means that this little window here where you see your plots isn't big enough. So just make it bigger. Let's try that again. All right, so there you can see the distribution of our data, very classically normal distribution, right? All right, so now we're gonna take some samples. We're gonna take some repeated samples from that population, see what happens to the mean of those samples. So we'll set the seed again, because remember you need to do it before every random process. And then we're gonna create some samples. So let's break down this code. Hopefully familiar to you, but it's always good to go over it again. So we're creating a variable called samps. It's gonna be a data frame. So in the data frame, we have a column called n, so that's our sample size. And we're gonna have 5 different sample sizes. So we have 1, 10, 30, 100, and 1,000. And then we are going to do something to every row, which is this row wise. And what we're going to do is we're going to create a new column called mean, which is the mean of a sample that's drawn from the population, so here, with the size of n. So for every row, which is this n, right, we've got 5 rows, we are going to sample from the population n times, right? So we're gonna have 5 samples from 1 to 1,000, and then the variable that we are creating is the mean of that sample, all right? And then what we wanna do is make sure that n is a factor so that we can plot it nicely. And so remember, a factor is just a categorical variable. And so you can, if I just run this, just so you can see, so there's our n, 1 through 1,000, and we're gonna do something to every row. Let's run that. So now you can see we have n, and we have our mean. So here we took one random draw from our population and took the mean, which is just gonna be the value of that one draw. Here we took 10 draws, and then we took the mean of those, on and on till we took 1,000 draws from the population, and this is the mean there. All right, so now let's plot that so that we can see what happens as we increase our sample size. So let's real quick go over this ggplot. So we're initializing the ggplot here, we're opening it. Then we're gonna add our geometries. So again, just plain histogram, we've done that before. It's just a histogram of our population. So that's, you know, these 10,000 values. And then we are going to add vertical lines for our samples, where the x-intercept is equal to the mean. So that means that each one of those means is going to have or that x-intercept of the line is going to be equal to that column mean. And then color indicates that we want the different lines for each end. So that means we're going to have 5 lines. Each one, the x-intercept is going to be its mean. I'll explain this in a second. I don't remember if we did that last time. And then here we also want to add in the population mean, so we can compare where those sample means are to the population mean. And here, I've just zoomed it in a bit so that you can really see where those lines are. So let's make this big again, and we'll plot that. All right, so let's take a look. So you can see this is our histogram. So again, if I hadn't zoomed in like that, you would be able to see the whole thing, but it's harder to see the differences in between these samples, although you can see that our N of 1 is way out here. And that's why you want large samples, right? Is because the more N that you have, the closer to that true population mean your estimate's going to be. Let's run that again. So now we can see here, remember we can't see 1 because it's all the way off here somewhere, but the black is the true population mean. And so you can see that this 1,000, this purple, is much closer to the true population mean than any of these other N's. Oh, and that's what I was going to explain there. So this key glyph equals path. The default for the legend here for these lines is for these to be vertical lines also. Let me remove this so you can see what I mean. And I just don't like the way it looks. See, it's hard to tell the difference. And so I just discovered this the other day and it made me very happy that you can specify how you want these little glyphs, pictograms, whatever you want to call them, to look. And so this path just means that they're going to be displayed sideways. And I just think that looks a lot better. I think it's a lot easier to read. All right, and so let's go through this again, but with our population being non-normally distributed. All right, so we're setting the seed again. And now, instead of our norm, which is the random draws from the normal distribution, this is from a uniform distribution. So our unif for random draws from a uniform distribution. And so uniform distributions just mean that every value between the minimum and the maximum have an equal probability of being drawn. So again, we're going to take 10,000 draws. Our minimum will be 0 and our maximum will be 100. Let's take the mean and let's look at the histogram again. So you can see it's pretty much just a rectangle, right? Because, and that true theoretical uniform would be a perfect rectangle because each value has an equal probability of getting selected. And so now we're going to do just, this is the same thing, but with our new population. So again, here are our different sample sizes. We're going to take the mean, make sure it's a factor, and then plot it. And so again, you can clearly see our 1 is way out here. And you know, you could get really lucky and that one random draw could be exactly your population mean. The point is, it's very unlikely. So the more draws that you take, the larger your sample size, the more you're just kind of shoring your bet, right? You're increasing the odds that you're going to be close to that true population mean. And you can see that here, that again, this purple line is the closest, the blue line is second closest, they're pretty close together. And then as you decrease N, you get further and further away from that population mean. And so now what we're going to do is look at the distribution of the sample means. So if we repeatedly sample the population and take the mean of those samples, what is the distribution of those samples? All right, so again, set your seed. And just by the way, this number can be any number. It's just a lot of people use 1, 2, 3, 4 because obviously it's easy to remember. It's just a good practice as a researcher whenever you set a seed to use the same number every time. And that way you don't forget. You don't want to use all kinds of different numbers because there's no real reason to do so. Like I usually use 5511 because that is the address of the house where I grew up. It's very easy for me to remember. So this can be personal to you. It doesn't have to be 1, 2, 3, 4. But for this lab, it's nice if we all use the same number. So we will run that again. And let's take a look at this code for a repeated sampling. All right, so again, we're creating a variable called samps. So hopefully you can tell that every time we have run this code, we are overwriting the previous variable. So if we wanted to keep all of these samples that we've created, we would need samps, samps1, samps2, samps3, because here we're overwriting this right here. So here, instead of the 5 discrete values for n, we are going to say we are going to take 1,000 trials. So this is similar to what we've done before. We're creating a column called trial with the numbers 1 through 1,000. You can see there. And then again, we're going to do something to every row. What we're going to do is take a sample from our population with an n of 100. So this time, every single trial has the same n instead of different n's. And then we're going to take the mean of that sample, right? So we're going to take the mean of a sample drawn from our population with an n of 100. So let's run that. So you can see here, so our minimum mean is just a little over 42, and our max is just about 59. And so if we, where is our population? So our population mean is 50 right here, which makes sense, right? Oh wait, did we? Yeah. Yeah, we're looking at this uniform distribution. If you imagine between 0 and 100, every number has an equal chance. The mean is going to be around 50, right? So now let's plot those means. So this is a plot of the distribution of the sample means. So we've got our ggplot. We're going to plot a histogram. So that's our geometry with samps as the data. And then what we want that plot to be of is the mean. And then we are going to put a vertical line for our population mean. And so you can see that even though our population has a uniform distribution, very specifically non-normal, those means of the samples that we drew from this population have a normal distribution, which I think is pretty cool. And again, that is one of the bases of inferential statistics. That's why we can say things about a population from a sample, is because of this central limit theorem. And it also relates to confidence intervals. When I was talking about the standard error, or the standard error of the mean, so the standard deviation of this distribution, the smaller that standard error, the more tightly those values, those sample means, are clustered around the true mean. And that indicates that you are more confident, you're going to be more confident in saying that the mean of a single sample is representative of the population. And again, that's why large sample sizes are important. And so confidence intervals are just the range of values that you can be confident contain the true value of a parameter. And so parameter being something that you are interested in about the population. So if we calculate the mean of a sample, that is a statistic. We are interested in the population mean, which is a parameter. So that confidence interval is going to be a range of values around that statistic, that calculated mean of your sample, saying I am confident to a certain degree that that true population mean is within these boundaries around the statistic. So I included a link to a video that I'd really like it if you watched. It's very short, but I thought it did a good job of explaining confidence intervals. So they can be kind of tricky to think about, I think. And so here is the formula for calculating the confidence intervals. And so there are a couple different ways that it can be done. And you will see maybe in class, in a lot of different literature, if you're reading about statistics, that there's one way to calculate the confidence intervals if you know the true standard deviation of the population. Almost always you don't, right? Because that's the point of sampling, is we really don't know anything about the population. We don't know those true values. So I gave you the formula for when you do not know the true standard deviation. So instead of using that, you use the standard deviation of your sample, which is an estimate of the standard deviation of the population. So the confidence interval is going to be the mean of X. So that's the mean that you calculate from your sample, plus or minus the critical value of Z that corresponds to your confidence level, times the standard deviation of your sample over the square root of your sample size, so n. And so again, the larger the n, the smaller this value is going to be. And so that means your confidence interval will be less wide. It means you'll be more confident. All right. And so here I have Z critical value. So you use that when your sample size is sufficiently large. So that is open to interpretation, what sufficiently large means. Most people take it to mean an N of at least 30, which when you think about it is not very much, right? So when you have a small sample size, so say below 30, you're going to need to use the critical value of T. And so that comes from the T distribution instead of the Z distribution. And so I put a little image here to kind of try and clarify why that would be the case. So here's our Z distribution. And so that's just that standardized normal distribution. Remember, it's a normal distribution with a mean of 0 and a standard deviation of 1. So this T distribution, which is what you're going to use if you have a small n, you can see that it's not as peaked and it has fatter tails, right? And so what that means is you are just giving it some leeway in terms of where those probabilities lie. It makes it a bit more uniform, right? Because we don't know as much about the distribution of that population if our n is small. And so as n increases, this T distribution approaches the Z distribution. And so a lot of tests, even what we're going to see here in R, just automatically use the T distribution because again, if your n is sufficiently large enough, it approaches this Z distribution anyways. But using that T critical value is always going to produce a more conservative estimate. And so you always want to err on the side of more conservative unless you have good reason to do so. And that just means that your confidence interval is going to be wider than if you use the Z critical value, which means that you're just a little bit less confident in your estimate. All right, hopefully that made sense. It probably didn't. I'm still trying to make sense of all this stuff, but please watch the video. And the more you hear these terms, the more you come across this stuff, the more sense it starts to make. And I tried to write this lab with these examples so that you really can kind of see it illustrated with data. All right. And so typically what people use for a confidence interval is 95%. So that means that you are confident that 95% of the time, so you take 1,000 samples, 95% of those samples, if you take the mean, that mean will be within a certain interval of the true population mean. That probably does not make any sense, but read this. So let's look and see what that means. We are going to create a new population. So we'll set our seed. We're going back to the normal distribution, mean of 100, standard deviation of 5. Go. And then we're going to set our n to be 100. So that just means we're going to take some samples of 100. Let's go through this again. Set the seed. And obviously you could have just written 100 here instead of using it as a variable. I'm sure I had some reason for doing that. So we're taking our sample from the population with size equals n being 100. And so our sample mean is close to 100, 99.6. All right, so we're going to take that Z critical value so that we can calculate this by hand. And so that Z critical value comes from this Q norm. So that means quantiles from a normal distribution. And it returns a one-sided value. And that just means that here, a quantile would be like right here if we do that, if we wanted that 95% confidence interval, that's going to be two-sided, right? There's going to be the high end here and the low end here. So we need both of those values. Q norm only gives us one. And so because these are equal, we are going to use a little bit more because this is going to, so we want the 95% confidence interval, which is going to be defined by two values, right? And so in total, this area in the tails is going to be 5% of this, right? So 5% of the values are going to fall outside of that confidence interval. And so that means that one of these values, 2.5% of the values are going to be here, 2.5 are going to be here. So to get this value, we need Q norm of 97.5 because that is halfway between 0.95 and 100. All right, so we are going to get our critical value, which we will call Z crit. So here we go. We will take the standard deviation of our sample because we need that too. There we go. Oh, I defined n here because we're going to need it in our calculation. How about that? All right, so now we are going to calculate those upper and lower bounds of our confidence interval. All right, so the lower end of the confidence interval, so down here, is the sample mean, right? So our sample mean, which we've calculated here, minus, because that's the lower end, our Z critical value times our standard deviation over the square root of n. And so remember your order of operations here. This will be evaluated first, This will be evaluated second because multiplication and division always take precedence over addition and subtraction. And so here the upper confidence interval is just plus instead, right? That's what this plus or minus means. So the lower end is minus, the upper end is plus. Run those. You can see those are our numbers here. And now let's plot. All right, so ggplot, histogram of our sample. We want one vertical line that contains our sample mean, and the color will be red. And then we are going to add two more vertical lines, one for the lower confidence interval, one for the higher confidence interval. And this line type 2 just means it's going to be a dashed line. And there are lots of other line types. Look it up if you want. Just Google search for ggplot line type. But we're just going to use dashed lines here. If you want to use something else, be my guest. Get creative. All right. And so you can see that this is our 95% confidence interval of the mean. So here is the mean of our sample, and this is our 95% confidence interval. And so what this means is that we feel, based on everything that we know about central limit theorem, the means, that this mean of whatever it is, 99.6, this area around it, this interval right here, is going to contain the true population mean 95% of the time. So another way to calculate those intervals is to use the t-test function. It's something that you can extract from the t-test function. You don't need to run this again if you still have it here. It's the same thing. I just put it back in here in case you were just going through and maybe you had erased your data or something like that. So let's look at this. So these are, we don't want to overwrite these because we want to compare them. So what this is doing is this is taking a t-test of our sample. And so a t-test with just one group, what we did before was a t-test of two groups. So it's comparing the difference. It's comparing the means, saying whether the difference in the means is significantly different from 0. A t-test with one group is saying, okay, well, is the mean of this group significantly different from 0? And so something that we can do, and I'll just show it to you here. If we just ran this t-test, and then let's print that. So here's our t-test. You can see that it, so one, we would accept this alternative hypothesis, right? Because this is a very small number. The true mean is not equal to 0. We would accept that. But you can see that it contains the 95% confidence interval right here. And so what we're doing is just extracting these numbers. Because if you look up here, X is our t-test that we ran. This is really just a list of values. So you can see the confidence interval is right here. So what we're saying with this $sign, we're saying is, okay, from this list, we want to access the confidence interval. And you can see that that's two numbers. So the lower end is going to be this first number. The upper end is this second number. And so you can see here, if you type in the name of your saved test and then put that $symbol in there, these are all of the things that you can extract from it, right? So you could take out the p-value, you could take out the test statistic, you want the confidence interval. And so if you just print that, you can see there are two numbers. To do this, it gives you the first number. This gives you the second number. And that saves you a lot of time. All right, so let's plot those. Oops. Need to change that because these should be other confidence intervals. Oops. So you can see it's the same, right? Essentially the same. If you compare them, you can see that they are just very slightly different. And that is because this t-test uses the t-distribution, right? It's in the name, comes from the t-distribution. Here, we're using the z-distribution. And so you can see our sample size was 100. That difference is negligible, right? That is not going to make or break you in any way. And again, as your n increases, these numbers will become closer and closer and closer. So I don't know about you, I think this is way easier. All right, and so we are going to do one more thing, and that is to kind of maybe better illustrate what these confidence intervals mean. So again, set your seed. Oh, these are still the same, right? Still the same population mean. So let's go through this. So what we're doing here, we're creating a new variable, or we're overwriting our old variable with a column called trial with numbers 1 to 100. Do something to every row. What we are going to do is, for this column, we're going to create a column called samp, and it is actually going to contain a list of every value in our sample. Because remember, columns and data frames, which are just vectors, can have any kinds of values, right? You can have a vector of lists. And so that is exactly what we're going to do. This is going to be a column of lists. And so what we're doing again is we're sampling from our population 100 times for each sample. So let me just run this so you can see what I'm talking about. So if you ever see this down here too, see how it just left that plus right there? That means you haven't completed your parentheses. So you can just add one more and it will complete. So now you can see for each trial, we actually have the list of the values, all the values from that sample. So here we go. We have, these are those 100 values that are in that sample. And then what we're going to do, and we're doing that because of the input, what you need as input to a t-test. We are going to create a new column for the lower confidence interval and a new column for the upper confidence interval. So this is just the same thing, right? We're doing a t-test of the sample. So each row, this is going to be different. And we want the lower value, the lower bound, and the upper bound of the confidence interval. So here you can see for each trial, we take a sample of 100 from the population, and then from that sample, we're doing this for each row, we get the lower bound of the confidence interval and the upper bound of the confidence interval. And so by default, the t-test uses a 95% confidence interval. If you wanted it to be something else, say 99% confidence interval, you would just specify that like this. I'll give you an example here. And so now we are going to plot those confidence intervals. So we're using our samples. This is just a type of plot that we haven't seen before, and it gives a range of values. And so here the X is going to be the trial. So which trial are we on? And then the minimum for the y will be the lower confidence interval. The maximum for the y value will be the upper confidence interval. And we want those grouped together by trial. And then we're also going to add a horizontal line for our for the population mean and color it red. So let's just look at it so it'll make sense. So these are those line ranges here. Oh, and I didn't set my seed. And since I'm sampling in here, this is going to look a little bit different. Maybe I should just go ahead and do that. There we go. All right. So you can see what this is there is a line for each one of our trials, 1 through 100. This is the true population mean right here in red. And then these are our confidence intervals defined by the lower bound and the upper bound. And so you can see, actually I think all of these do. I didn't set all my seeds right. Let's look at this one. You can see, and here we got lucky, right? But that about 95% of the time, these confidence intervals contain the true mean. Sometimes they don't, right? You can see that here. Because that's random, we're taking random samples, but for the most part, the confidence interval is going to contain the true population mean. And so that's why we can say when we take a sample, when we take the mean of that sample, we calculate the confidence interval, we can say, okay, we are pretty confident, we are 95% confident that this sample mean is representative of the mean, the true mean of the population. All right, and then you go through some exercises here. I need to renumber that. But so please, when you are writing your code, make sure and number your exercises with hash marks, make them comments. It's just a lot easier for me to grade. It gets pretty dense reading these scripts, so it's very helpful if you kind of block off your exercises. And it's really just going through exactly what you went through in the lab, except instead of using a uniform distribution or a normal distribution, you're going to use an exponential distribution. And you will be able to see what that looks like, if you don't know already, when you start working on the lab.